We are creating perfect squares, so we need to create numbers with exponents of the primes in the prime factorization that are even. So we are going to be considering the parity of the exponents that get labeled on the sides of our cube. First, I want to show you that the opposite sides of the cube, the corresponding primes, have to have the same parity. Let's look at an example where the top and bottom opposite sides of the cube have primes which do not have the same parity, such as 2 to the first power, which has an exponent that is odd, and on top we'll put 2 squared. In order to create a perfect square at vertex A, we need to have the product of the front side and the right side to yield a product with the prime 2 raised to an even power. In order to create a perfect square at vertex B, we need the product of the front and right sides to have a power of 2 that is odd. The product can't be even and odd at the same time, so we can't have A and B both be perfect squares at the same time. We need all 6 vertices to be perfect squares. So let's take as our first case, the top and bottom have even powers of 2. The smallest even powers are 2 and 0. We'll put 4 on top and 1 on the bottom. You'll notice that all 4 sides of the cube will have to have either 2 raised to an odd power or 2 raised to an even power. We'll treat these as 2 separate cases. If we limit ourselves to 1 prime in the prime factorization of the faces on the sides of our cube, and those primes are odd, then we can start with 2 to the 1, 2 cubed, 2 to the 5th, and 2 to the 7th. The sum of all 6 sides will be 175. If we allow ourselves a second prime in the prime factorization, so we'll use 3 since it's the next smallest. Our odd primes we can reuse 2 to the first power and 2 cubed, and we can combine them with these powers of 3 to create 4 different numbers. The sum of all 6 sides here is 105, so we beat our case with 1 prime. Let's try assigning numbers to the sides of our cube where 2 in the prime factorization is raised to an even power. That's case 1b. If we limit ourselves to 1 prime, the first 2 even powers of 2 have already been taken, so we are left with 2 to the 4th, 2 to the 6th, 2 to the 8th, and 2 to the 10th power, which is way bigger than what we started off with 105. We're trying to beat 105 right now. If we introduce our next smallest prime, so now we have 2 primes, we can reuse 2 to the 0 and 2 to the first power and combine them with powers of 3 to generate different numbers. But again, we see that we have one side with a number 108 on it, and that's way too big as well. So we can stop with case 1b. Now we can consider trying to beat our sum of 105, where we have the top and bottom faces with the 2 smallest odd powers of 2. That's going to be 2 cubed on top and 2 to the first power on the bottom. In order to generate products at A and B that have even powers of 2, we need to have the 4 sides of our cube alternate in the parity of their powers. So if the front face has an odd power of 2, the right side of our cube has to have an even power of 2, because then we'll have an odd and then an even and an odd. Odd plus even generates an even power, which is what we want in order for vertex A, for example, to be a perfect square. If we limit ourselves to 1 prime with alternating parity, We can start with 2 to the 0, 2 to the 5th, 2 squared, and 2 to the 7th as the powers that we haven't used yet. And again, one of these sides is already too big, so we can stop here. Let's try 2 primes by adding in 3. Now we can alternate the powers of primes, but we can reuse 2 to the 1 and 2 cubed in our alternating powers by just multiplying each of these by 3. The sum of these 6 sides is 55, and I'm fairly confident that that is the minimum sum.